All right. I know it's past midnight, but I feel like this might take really not much time, so let's just get on to it. Um, yeah. So, mass spectrometry. I'm sure you guys know what this already is to some extent, considering there's a diagram of how this apparatus kind of works right here. So if you notice, basically what it does is you're basically putting a gaseous sample. Oh my god, yeah, you're putting a gaseous sample as indicated here, vaporized sample, and you're basically shooting high energy electrons at it and then ionizing it to separate things essentially. So think about it like this: you're converting it into ions and then deflecting it by a strong magnetic field, and then basically what happens is each compound has a different mass to ion charge ratio, right? So they each get a different amount of deflection, and this ion detector right here will actually detect very precisely what mass to charge ratio each of these compounds have. And you'll see later on, but the higher resolution mass spectrometry gets this really accurately, so you can identify virtually any compound using mass spectrometry. So that's basically what it is. There's not really much we should go into complexity here because, there's not that many questions on it. But giving an example of what you can use it for, you can use it to determine isotopes. So this relative abundance thing right here is basically every single atom, right? Every element has isotopes that occur naturally, and what you're basically doing is you're splitting up a sample into its isotopes based on their mass to charge ratio. Because think about it, isotopes are basically the same element, right? But with different numbers of neutrons and the same number of protons. So the more neutrons you have, the higher mass to charge ratio you will have, since the charge remains the same, but your mass increases. So that's basically what this thing is right here. And as you can see, for in this case, for lead, the most common isotope right here would be lead 208, which would be written like this. And the other ones would be, let's see, the next most common one would be PB206. Oh my god, that was so bad. PB206, and then etc. with 207 and 204. And as you can see, there's none for 205 and 209, so that's not really important. But moving on, as you can see, relative abundance always adds up to 100, because if you split something up into its pieces, all of them have to add back up to make a whole, right? So that's the most common way you can do it, and how you determine the relative atomic mass from this data, right? All you have to do is, yeah, as they say, multiply each atomic mass by its percentage abundance, and then add the figures together and divide by 100. So an example of this would be here. For lead, let's use violet this time. What you would do is, they give you this data right here separately, and they also give you this isotopic mass. So what you would do is they say add them up and then divide by 100 at the end. Honestly, you could do that, or you can just convert to a decimal. That's the whole point of the dividing by 100 anyways, to get the percent. But basically what you would do is 0.02 times whatever the mass of that component is. So in this case, it would be 204, plus 0.24 times 206, plus 0.22 times 207, plus 0.52 times 208. And adding that all up will give you your final mass. And I don't have a calculator on me, but if you were to sum that up, that's what you would get. And of course, you can also confirm whether you're correct or not by looking at the periodic table. But yeah, that's basically how you do atomic mass. This one's not really that hard, it's just kind of simple math. But it gets a bit more complicated when it comes to a different form of mass spectrometry, which is what happens when you split it up into ions. So again, same case here. Again, you just do 0.909 times this mass right here, 20. This would be 0.003 times 21. And then that would be right here, 0.088 times 22. And if you were to add them all up, you'd get the relative atomic mass, as you can see right here. But yeah. And of course, sig figs, make sure you don't forget them. And as they say right here, a higher resolution mass spectrometer can give very accurate relative atomic masses. So, you know that oxygen is this apparently 15.995. I did not know that, so never mind. And sulfur is 31.972. So that means that when you're looking at SO2 and S2, which if you were to estimate them, they would get 64 and 64 if it's low resolution, right? But since this is high resolution, you'd get, 2 times that plus that versus 2 times this. But you get what I'm saying. Point is, you get more accurate decimal places, and higher resolution mass spectrometers go to even more. And I'm pretty sure some of the most advanced ones can get to up to 10 decimal points, maybe even more. I'm not sure. Don't quote me on that. Now we come to organic chemistry. So this is where it kind of gets complicated. If you have CH3, CO, CH3 like here, right? If you were to draw that out, what does that look like? You get C, H, H, H. Then you get a C, the one O, C, H3, like this. That is propanone right there. Oh, I didn't see that. That probably would have helped. But that's propanone. It also looks like this if you know skeletal formulas. Pretty simple. Basically, what this does is, notice how they're splitting up into these different zones, right? What this is think about it like shooting an energy wave that goes something like this. Boom. Cutting it up into CH3 plus, and then, I don't know, COCH3 plus, like that. What this means is, what is the atomic mass of this? Well, you know that it would just be 12 on the carbon, and then 3, because each hydrogen is 1. So this overall would be 15. Meanwhile, this right here would be, let's see, 12, 16, that's 28, another 12, so that's 40, 43. This would be 43 right here. And if you can see, this peak right here corresponds to 15. So this right here would be CH3 plus, whereas this peak right here would be COCH3 plus. Does that make sense? Hopefully that does. Basically, match the masses up with the fellow masses that you find here, and that's how you get it. And then you might ask, then what is this 58? Well, what happens if you add up 15 and 43? Yep, you get 58. So this right here would be the peak for the original compound, which would be propanone. And that is how that works. And let's see, I'm pretty sure they discuss this a bit further, but that's basically the gist of it. Just imagine it as splitting it at a bond like there, and then moving on like that. Anyways, sorry for the screen moving and all. Again, this is just another one of those mass spectrum for an element. I can kind of move on from that. I'm pretty sure you guys know how to do that now. And as you can see, splitting comes from removing an electron like that. That is the definition of ionization, which is what mass spectrometry is doing. You're ionizing a compound that is in its gaseous form, and then you're using a magnetic field to deflect it. That is how, by the way, you get these different peaks. This relative abundance, they're splitting it up by using the magnetic field, which is how they're getting this mass to charge ratio, because that magnetic field is predetermined. And yeah, anything that's of that form, like for instance CH4 plus there, is called the molecular ion, and it's denoted with an M plus, right? And again, it's kind of self-explanatory. Like in the previous example that I just showed you, basically cutting it at that bond right there, and then you're forming this. So yeah, so you get plus and a plus, and then obviously you get these two separate compounds like that. Pretty good. That's really all there is to it, and obviously that's why you get that relative mass of 58, and then they're splitting it up into 15 and 43, as I said before. And moving on, you can kind of memorize these because they're kind of common. For instance, if you get 15, no matter what it is, it's always going to be CH3 plus, because think about it. If you're splitting up an organic molecule, right, and you only have one carbon on it, you're always going to get a carbon and then 3 hydrogens, and then that's going to become 15. Obviously, if you have something else, like for instance, if you're splitting up, I don't know, say you're splitting up something like this, I don't know, maybe OH. If you were to split it up like that and that, then sure, you'd get 13. But really, will anyone ever give you a lone oxygen that's 16? No, I don't think so. Point is, it's just math. Use kind of common sense. If it's 15, 12 plus 3, because carbon and 3 hydrogens, it's probably going to be an ion for for methyl, I guess. Yeah, methane. And yeah, same case here. As you can see, 43 could be that or that, whereas 15 is going to be this. So yeah. And that's why they have this section, by the way. This is important, because these are the very common in mass spectra. You don't really need to memorize these, because, you can induce it from common sense. But again, you've got this, CH3+, and then moving on to the next page, you've got CO and C2H4. Okay, alkenes are kind of common, so are carbonyls. They're both kind of well to know, especially since 28 is, kind of common to see. But if they ever split it up like that, you'll get that. But most typically, since this mass spec is AS level, they'll always split the compound up into two separate ones. So for instance, using this example right here, C2H5OH, what they would probably do is they would do let's see, if we were to draw ethanol real quick. Sorry, I'm covering up the kind of covering up the question, but if you ever get something like this, right? Typically what they do is they probably cut it like right here, and then they won't cut it up further. Like they won't ever cut up that other one. So typically speaking, they'll generally cut it up at the bigger one. They're always going to try and give you the CH3 part right here. Hence why 15 is such a really good one to know. And then yeah, after that you can kind of figure it out. So, for instance, the ACE exam, if you took it this year, the paper 2 had a question where you split up, I think it was 2-pentanone. Yeah, you basically split up 2-pentanone into two separate compounds. They wouldn't split it up further. But yeah, so continuing on. Sorry, I'm going a bit of a tangent here out of order. 29 would be this, which is just, ethane, I guess. Yeah, ethane ion. Same, in this case would be, what is it? Propane ion. And then this one would be a methyl ketone ion, I guess. Yeah, point is, these values are good to know. You don't have to know them, though. But they're pretty helpful. So, let's just quickly go through this question, I guess. Methoxymethane with the formula like that. Okay, so that would be, here, if we were to draw a skeletal, that's what it looks like. Yeah, that's really all there is. Predict the mass to charge ratio of a fragment that would appear in the mass spectrum, but does not appear on ethanols. Okay, so like I said before, you could literally just cut it at that place. So you could cut it again like that, and then this piece right here would be unique compared to this piece right here. That's not really that hard. Okay, the formula of the ion responsible for that peak, again, it would just be OCH3 plus. Again, not that complicated. Look at the mass spectrum for ethanoic acid and identify the fragments. 15, 15, 43, 43, 45, 45, 60, 60. Again, just match up the numbers. It's not really that hard. Now, this, again, you don't really need to know. They're just, again, going to more decimal places. Not really complicated. Yeah, and then, again, more accurate. So you can distinguish between these two compounds. And yeah, anyways, continuing on from that, the N+1 peak, all you can do is, let's see, this formula right here, right? Here. This thing right here is of the utmost importance when it's coming to using mass spectrometry. So why is this important? Basically, you're using carbon-13. So carbon is composed of two main isotopes. There's the more common carbon-12, which is what we are all known for. That's what the AMU is based off of, and carbon-13. And I'm pretty sure you guys heard of that as well because of carbon-13 dating. So why this is important is you can actually determine the ratio between these. As you can see right here, it's 1.10%. Yeah, so you can actually use this formula right here, which is basically determining that ratio, and then using this N+1 ion, which is, again, to get from here to here, it's +1, hence the N+1 ion, and then the abundance of the N+ ion. And you're using this ratio to essentially determine the number of carbon atoms that's in the molecule, right? So an example would be, like they give here. Yeah, actually, wait, here. Yeah, never mind. I was trying to find something that wasn't there. But yeah, relative abundance of 54.5%. That would be this value right here. And then it has an m plus 1 peak that has a relative abundance of 3.6. So again, m plus on the bottom, m plus 1 on the top. And then always 100 over 1.1. That one always stays the same. So doing that, you get 6 carbon atoms. So why is this very helpful? Well, if you ever get a question where they give you this relative abundance, like ratios like that, and then they ask you for like, let's say, I don't know, maybe they give you a peak of maybe this value right here, I don't know, and they say, what could it possibly be? Or actually, no, never mind, ignore that peak. Let's say it's this peak. And they give you the mass charge ratio, which is like, let's see, if you zoom in, that's like 31, right? So you can use that, and then you can get this number of carbon atoms, right? Well, you can also deduce the splitting of this thing right here by saying, oh, maybe the graph shows that there's, I don't know, there's this CH2OH plus, and then maybe the other one shows that there's a C5H12 plus, like that. In this case, you deduce that the compound that you're looking for is one hexanol, right? 1, 2, 3, 4, 5, and then an OH, like that. Because it would basically be splitting it at this bond right here. Hence the C2OH plus and the, well, CH2OH plus and then the C5H12 plus right there, which would be this thing right here and this thing right here. That's why this is helpful, because you can determine the structural formula by coming up with this. So that's pretty cool. We don't really need to know this stuff, n plus 2 peaks and n plus 4 peaks, but I guess they're pretty cool to know. But yeah, also, just a quick side note before we move on. N plus 1 peak is always right after the largest peak that you have. So in this case, they were doing the graph for ethanol, which is C2H5O. Well, C2H5OH, which is, again, this compound right here. And this N plus 1 would basically just be the carbon-13 peak for that, hence the plus 1. Which is pretty cool in my opinion. M plus 2 and M plus 4, on the other hand, they're used for chlorines and bromines. So again, this isn't part of the syllabus, so you don't need to know it. But basically what they're saying is if you have a ratio, like for instance, if the M plus 2 peak is 1/3 the height of the M peak, then there's a chlorine. And if the M plus 2 peak is the same height as the M peak, then it's a bromine. Again, you don't need to know this stuff, so I'm not really going to go over it in depth. And then, yeah, there's some other stuff too. Again, you don't need to know it. If you want to know more about it, I suggest you just read it. Here, let me just slowly scroll through it so you can read it if you want. Pause the video at any time if you want. And then moving on, it's this. And that's really all there is to it. As you can see, there's a crap ton of peaks. Ignore those because they're not really that relevant here. But yeah, basically what they're saying is if you have these peaks, those ratios will, here, you'll basically see these ratios here. So if you can see, that is about 1/3 height of the biggest peak, meaning there's one chlorine, and etc. You could also do that for bromine. Again, I'm not going to go over this that in depth because we don't need to know it. And yeah, that's it. That is mass spectrometry in a nutshell. So again, quick recap. Know how to do this stuff. Again, it's literally kind of simple math. They'll either give you the value in a table like this, or they'll give you it in, actual labels like this. Either way, just convert that number to a decimal because, it's a percent, and then multiply it by the mass charge ratio that they give you. Again, as you can see here. Do that, add them up, you'll get your final value, as in this case. Meanwhile, for organic compounds, just basically think about it as splitting a bond and then forming two separate positive ions. And then do that. So in this case, again, splitting it like that. So you get CH3 plus, CH2OH plus, etc. And then, of course, just find the mass of the overall ion. Again, the plus doesn't really matter. All you have to do is count up the individual atomic masses of each compound. So again, oxygen 16, carbon 12, hydrogen 1. You know, those are really the only ones you need to know, except for maybe nitrogen 14. But yeah, once you know those, it's kind of simple. After that, remember this key formula right here. This one here, let me zoom in on it. The 100 over 1.1 times the abundance of the n plus 1 peak divided by the n plus peak. And yeah, I felt like doing this because, I'm kind of not that tired. And I know we had an ACE exam today, ACE paper 4 for US history. But yeah, I felt like doing it. Hopefully, this clears up your understanding for mass spec. Um, that's it. So yeah, again, this could come up in paper 1. I'd say there's probably going to be a question on it, and it won't be this advanced organic chem. I'd say you probably won't need to know this. I'm assuming it's probably going to be one of these simple questions. But yeah, the more you know, the better. Anyways, that was mass spectrometry. It's been a while since I've uploaded, so there you go. Hi again if you're returning, I guess. Um, yeah, I'm also going to start a series soon, basically solving every single paper 1 in existence from 2016 onwards. So get ready. All right, well, I'll see you later. I should probably go sleep now. Bye.